Okay, Assalamualaikum and a very good morning.
Salam, sir.
Okay.
Masalah.
Okay, so I think we just continue the lecture. So we still in the lecture 4, topic under force vibration for the undamped system, single degree of freedoms. Okay, so for the yesterday sessions, we stop at the rotating unbalanced force, so which is one of the common force that induce the system with the harmonics pattern. Okay, so now we look at for the examples. Example how to solve vibration problems that relates with the force vibration. Okay, so this is a reciprocating pump, which is the mass is equivalent to 68 kg. It's mounted at the middle of the steel plate with the thickness of 1 cm with 50 cm and the length of 250 cm. Clamp along the two edge as shown in figure. So which is basically this steel plate. Okay, so we can treat as a spring lah. Okay, so under boundary condition fits cantilever beams. Okay. And the dimension is given. Okay, however, you have to first convert into SI units. Okay, then during the operation of the pumps, the plate is subjected to the harmonic force. So which is when the pump is in the operating, it induces the force which is equivalent to 220 cos 62.8 V2 T newtons. Okay, so from this information we can extract the information of the force induced. Okay, so 250 is F naught here, which is the magnitude of the force, but it's fluctuation based on the cost function. Okay, so this is cost function, which is the frequency of excitation in radian over seconds is equivalent to 62.8 V2. Okay. Find the amplitude of vibration of the plate. Okay, so for this case, when the question asks to find the amplitude of vibrations, so mean that you only have to solve the x value lah, so which is the x capital. So in this case, there is no initial conditions given, so mean that you just have to consider the steady state response. Okay, so steady state response is just based on the direct equation lah. So if we refer back, refresh back, so it's based on this equation lah, or you can take as a F naught K minus M omega square. Okay, so what the information we need is the F naught, the stiffness, mass, and also the omega. Okay, so back again to the questions. We already have the mass. F naught is given, omega is given, but stiffness is not yet. This not directly given, so you have to calculate. So based on the geometry of the steel plate, okay, under boundary condition fits. Okay, so to find the first, we need to find the stiffness of the beam lah. Okay, so this is the general equation. Okay, general equation for the fixed steel beam. Okay, so which is the properties of the beam, which is Young modulus 200 gigapascal. Okay, so the length, the moment of initial you have to calculate lah. So make sure all the units must be converted into SI units. Okay, so this one is IV moment of inertia. Okay, and then put it into the equation. Now we can uh, determines the stiffness for the beam. Okay, then begin to calculate the amplitude just straightforward using the equation lah. So this exercise just to make sure that you get familiar with the equation and how to use the equation lah. Okay, so for this case, this is force vibration. Okay, so force vibration, the response normally for the undamped we are only interested about the amplitude lah. Okay, so because the frequency should be same with the excitation frequency. Okay, so F naught based on the given formula, so it's a 220 K. When they calculate M is a given lah. So the question 68, and then this is omega. So omega is depend on the excitation frequency. So 62, which is already in the radians over second. Is the question give you in the unit of hertz, then you have to convert lah. Omega is equivalent to 2 pi f. Okay, so after you solve this part, then found that uh, there is a negative sign here lah. So actually the negative is represent the direction of the motion lah. Okay, so which is negative represent the out of phase. So mean that it goes to the different direction to the applied force lah. Okay, so if force applied in the upward, and then the mass will move to the downward lah. Okay, so it's opposite direction. So meaning that for this case, the excitation frequency here is greater than its natural frequency. Okay, now looking for the example for system shown in the figure. Spin mass system. Okay, so with force excitation, harmonic force excitation. Okay, so the properties of the system: mass is 10 kg, stiffness is 4 kilonewtons over meter, harmonic force is 400 newtons magnitude with the frequency of 10 radians over seconds. So applied to the system, so we just add to the system. Question asked to determine the total response. Okay, so the total response, okay, when you talk about the total response, you have to consider the particular and homogeneous solution. Okay, and if you follow step by step, at the first place you have to solve the particular solution, and then after that you complete the equation, insert all the initial conditions that given, and then find the unknown value, the remaining unknown value. Okay, see, actually for this solution, simple. So the question is the system a bit simple. You can either use a direct equations, okay, or you can you can do manual if you don't remember the equations. Actually, you can just represent into this equation as xt equal to a cos omega n t plus a. Sorry, sign. Okay, so that's the common solution. Okay, so which is more universal. Okay, so the first step you solve for the x. Okay, so first solve x. Okay, so this one you can just using the equation lah. Okay, so using the equations, so f naught k minus m omega square, so f naught is 400. Okay, and then uh, stiffness, mass, and also the omega lah. So solve it, and then you can solve this part is a particular solution lah. Okay, so this one is a xp, and then this one is a it's h homogeneous. Okay, so then next you insert the initial condition lah. Use x naught and x dot lah. Okay, so but the second part you have to differentiate lah. So you have to make it another equation of the velocity. Okay, so which is this one is a minus a sine, oh sorry, omega n omega n sine t, so plus b omega n cos omega n t minus x omega sine omega t. Okay, so so based on these two equation, okay, so you insert all the value lah. Okay, so all the value when t equal to 0, and then you got these equations. Okay, so you will have a two equation with two unknown. So unknown here is a and b lah. Then the third you solve lah, solve a and b. Okay, so this one is the more general solution lah. Okay, however, if you know the system is very simple, you can straightforward using the equation lah. This equation is general equation for the single degree of freedoms. Okay, so based on the given initial condition, you can just insert from this equation. If you use the same step, you can also get the same solution lah. Okay, so from this equation, okay, so you know that we don't have a sine function because initial velocity is equivalent to 0 lah. So here, so I mean that there is no initial velocity here, so it's equivalent to 0. Okay, so that's why it's cos. Okay, so this one is particular. This one is particular, and then this one is a steady state. The homogeneous or transient. Okay, so you have to know how to differentiate lah. For the homogeneous, you use omega n instead of omega lah for the particular solution. So it's 20 omega, 20 omega n, 10 is omega. And the rest almost same lah. Okay, just insert initial condition, the rest already calculated. Okay, so the most important thing here, what you have to know if you have a questions, if the question given initial condition, so when that you have to consider the total response. If there is false and there is initial conditions given, then you have to solve the total response. But equation asks to solve the particular solution, then you just have to consider the particular solution. If the question just stated that you have to find the vibration response, so vibration response is equal to x. Then if inside the questions given the initial condition, you have to consider the total response. If the question did not give any information about initial condition, then just consider the particular solution. Okay, then this is the isolation study. Okay, so isolation study actually is part of uh, the mostly used in design stage lah, to reduce the vibrations. So basically uh, the isolation is we want to isolate the vibration motion from the transmitted to the other structure. Okay, so basically if you have the vibration source, okay, so which is produce the vibration. For example, there is a motor or the engines. You want to isolate that the vibration from the motor or from the engines from transmitted to the other structures. Okay, so actually there is a lot of factor to be considered. Okay, so is either you control the speed or you control the properties of the structure. Okay, so first example for the transmission to structure from so which is under vibration force excitation. So we want to reduce the force transmitted. Okay, so when the equipment in running conditions, especially for the rotating machinery, it's induced the force lah. For example, there is a when washing machine is you running the washing machine, you know that the mass is not well distributed from your clothes. So mean that it's create the unbalanced situation. Okay, so when there is an unbalanced mass for the rotating equipments, it will induce the rotating force lah. We call as an unbalanced force. Okay, so that's unbalanced force. We create the vibrations. Okay, and then the force will be transmitted to the structure or any support structure lah, where you put your washing machine, and we transmitted lah. Okay, and then this is the force created by equipment, and then this is the structure. So how much the force is transmitted to the structure. So basically it depend on the how much displacement of the equipment itself lah. So the washing machine, how the washing machine is have a displacement. Again, because between washing machine and the support structure, there is a damping or the stiffness elements. Okay, so basically dominate by stiffness elements. So higher displacement, the reaction force from the spring we react to the body. Okay, so basically to isolate the system, to reduce the force transmitted to the other structure, the solution is we must reduce the magnitude of the vibration, so the amplitude of the vibration. Okay, so this one, we look at the equation after this. And there is also the other, okay, so another example is car, for the car structure. So we know that the engine is, when the engine in motions, there will be vibrations, okay? It's induced the vibration, okay? So for the comfort study, we must ensure that the vibration from engine is must be minimum to the car body to avoid the user receive that kind of vibration. So now we still in the undamped system lah. So the undamped system, actually we just looking for the spring and mass factors lah. But in actual there is another element which is damping elements lah. Actually damping elements is one of the most important for the isolation study lah. It's something like the engine mounting, so it's considered the mount the damping elements itself lah. Okay. But however, we still can control the vibration based on the spring mass and also the excitation speed lah. Because we know that um, uh, the amplitude of the force vibration is depend on the F naught over K minus M omega square, right? Okay, so K is stiffness, M is mass, and omega is excitation speed. So that three parameters or three variables that control the level of vibrations. And then the second part is a transmission equipment to the equipment lah, from the ground excitation. Okay, so which is the structure have a motion and then transfer to the equipment. For example, this one is the electronics components lah. So if there is vibration from the body of electronic equipments, you want to design something the transmitted to the other component inside that equipment is a minimal. So that is why we study about the isolation study. We want to isolate that system to ensure that it doesn't transmit it to others, or if others vibrate, it doesn't transmit it to the equipment. Okay, for the spring mass system, okay, the force transmitted is is proportional to the amplitude of the oscillation. So which is the amplitude of the vibration and the force excitation is proportional to the force transmitted lah. So because for example, this mass is linked to the other structure with the stiffness elements lah. So which is higher displacement for this mass, the higher force transmitted at this point lah. Okay, so the vibration force at the end of the spring. Okay, so that's the concept lah. So if you want to reduce the vibration, you have to reduce the A. Okay, so the A value here. Okay, so in the isolation study, there is the parameter we call as a transmissibility. Transmissibility is which is the ratio lah, the transmitted force over the magnitude of the induced force lah. Okay. So basically, we know that the force transmitted is depend on the amplitude lah. So F equal to K KTA lah. So KA, A is amplitude. Okay. Okay, and then F is the force applied lah. Okay. So basically, the amplitude here can be represented as a F over K minus M omega square. So after you play around with the equation, you will get this relationship. Okay, so which is transmissibility, T is equal to Ka over A K minus M omega square. Okay, so which is this one can be simplified into the formula 1 over 1 minus omega over omega n. Okay. So which is this one we can call as the frequency ratio, the ratio between frequency over omega n, excitation frequency over natural frequency. Okay. So that's the transmissibility, how we measure how much is force transmitted lah. If transmissibility is greater than 1, so meaning that the force transmitted to the body is greater than the force induced to the system, so which is not good lah. So because we want to make it minimum, even it produce the high forces during the operating, but the amount of transmitted to the body is less than that. This one is a that thing that you can consider lah to control the vibration. Okay. Okay, so based on the, that the response, okay, so when the omega, okay, so the omega over omega n is equivalent to 1, so which is the excitation speed equivalent to natural frequency, there is a resonance, okay, so resonance, so it's 1 here, so which is this one, you have this one is static condition, so when you increase the speed until it reach the natural frequency, then you have the infinity amplitude lah. So you keep increasing, and then you start reduce lah. Okay. So to control, okay, so to ensure that the transmissibility less than which is the force transmitted is less than the excitation force, so we have to ensure that transmissibility is less than 1. Okay, so which is could be found at this point. So negative here actually is referred to the direction, so because this one is a positive in phase, okay, after 1, so which is if you excite the frequency excitation greater than natural frequency, then it goes to negative lah. So negative until it reach the -1, so mean that it's equivalent, and it's more than that, it could be lower than the transmissibility will be lower than 1 lah after that. Okay, but of course it goes to the opposite direction lah, so which is the out of phase. Okay, so based on this relationship, so when the transmissibility is -1, so the frequency ratio equivalent to square root of 2 lah, which is 1.41. Okay, so which is at this point, so mean that if you excite the frequency excitation is greater than 1.41 to be precise, and then if you excite greater than that, the force transmitted to the structure should be less than the excitation force. So that's the concept of the transmissibility. So it's meaning that you can change the operating speed lah. So you can change operating speed. If that's a very favorite question actually in the exam. So if given the example, if you want to ensure that the force transmitted less than the excitation force, so you have to ensure either you change the operating speed, which is should be greater than 1.4 frequency ratio, or otherwise you still can control the K and M lah. Okay, so K and M actually you can change the natural frequency lah. You change the stiffness, you increase the natural frequency. So basically, if you want to reduce, normally we control the mass lah. So which is you add another mass. Okay, you add mass to the system, and then you can move this frequency to the your left hand side lah, so you can reduce. That's the solution lah. So actually, I prefer you are using this equation lah instead of this one. So if you want to control the speed, then it's okay. You can control this one, okay. And then if you want to find the other solution, which is you can still control the k, m, and omega. Okay, so you can use this equation. Okay, so look at example. A 400 kg exhaust fan with a 0.15 kg meter rotating unbalance is supported on 4 parallel springs. The weight of the exhaust fan resulting in a 50 mm deflection to the spring. If the fan is running at 1500 rpm, determines the amplitude of vibration, the force transmitted to the ground at each supported spring. Okay, so this is uh, example of the force transmission lah. Okay, so for this case, first question asks to find the amplitude of vibration. So again, you analyze the question, and then from this question, there is no initial conditions given. Okay, so which is in this case, the amplitude of vibration, you have to consider only the x okay, the amplitude of a particular solution. Okay, so which is x is equivalent to f naught k minus m omega square. Okay, so f naught is not given, okay, but this one is given the information of the rotating unbalance. Okay, so we know that the rotating unbalance f naught is equivalent to mu e omega. Okay, so this one, okay, so 0.15 kg meter rotating unbalance actually is referred to the mass of the unbalance times by the distance. Okay, the distance unbalance mass to the center of rotation. Okay, so which is, if you refer to the equation, mu times by e lah. Okay, if you want to refer to this one, okay, so this one mu e, so mu is mass times by e distance. Okay, so the value is already calculate. Okay, so the weight of the, okay, so now we can calculate for the f naught lah. Okay, so to calculate f naught, we need the information of omega. Okay, so omega here is not directly given in the unit of radians over seconds lah. So if given in the unit of rpm. Okay, so the rpm 1500. Okay, and then you have to convert lah. So omega is equal to 2 pi f. Okay, so frequency equivalent to rpm over 60 lah. Okay, so divided by 60. Okay, so you got 157.08 radians over seconds. So now we have the omega. Mass is given. K, okay, K is not given. Okay, so K is not given. However, it gives the deflection. Okay, so which is under the weight of this exhaust fan, it deflect 50 mm. So from that, actually we can relate with the Hooke law lah, to find the stiffness. Okay, so which is F equal to Kx. Okay, so F here we can represent the weight of the fan lah. So mg, so mass times by the gravity. Okay, so the deflection is already given, but unit is mm. First we have to convert, and then you can, from that you can calculate the stiffness. Okay, so now K equivalent is equal to omega over delta X lah. So delta X you have to change into SI units, which is you can find that the equivalent stiffness is a 67.48 lah kilonewtons. Okay, and then the F naught. Okay, so they calculate. Okay, so the stiffness, the question given that is supported by 4 spring in the parallel arrangement. So mean that stiffness for each spring can we just divided by 4 lah. So this one is the stiffness for each spring. Okay, and then the amplitude of vibrations. Okay, so the amplitude of vibration, actually you have to consider the total spring lah, the equivalent of the spring. Okay, and then F naught over K minus M omega square. So F naught calculate. Okay, so which is 0.15 times by the omega. So omega we have already calculate here. Okay, so omega. Okay, so omega square lah. Then you can get the F naught, so which is the magnitude of the force. Okay, then just insert into the equation. Okay, so then you can get the X. So the negative sum here, so meaning that there is a out of phase. Okay, so this one is the total amplitude. Okay, so total amplitude, which is the motion for the exhaust fan. Okay, and then the B question asks to find the force transmitted at each supported spring. Okay, so we consider that each spring have the same deflection. Okay, so which is for this case, instead of K equivalent, you must use K lah. K times by the amplitude. Okay, so this is what you get lah. So equivalence to the stiffness times by amplitude. So they need in the Newton lah. So make sure that all the unit in the SI units and then you can just straight away can get the answer in the SI units. Okay, I think that's all for the force vibration. Okay. So chapter 4, and then we have another chapter, okay, which is covered in your midterm exam lah. Okay, so